So in graphing exponential functions, we're going to look at graphing them. There's two categories. And the first category is when your base number, so if I have f of x equals a to the power of n, so the first category is when a is greater than 1. So for example, 2. So if I have f of x is 2 to the power of n, well actually I'm sorry, why am I saying n? It's got to be x because we're talking about a function. A to the power of x, so our example, we're going to graph 2 to the power of x. And so to graph this, when our base is greater than 1, for our example, we're using 2 to the power of x. Let's make a table and plot some points. And so we have our input, and then we have our output, which is 2 to the power of x. Now, typically, the most interesting stuff on a graph happens close to the origin. And so we're going to look at the values from -3 to +3. And so 2 to the third power, starting at the bottom, 2 to the power of 3. This literally is 2 to the power of 3, so that's 8. Then we have 2 to the second power, 2 squared, which is 4. 2 to the power of 1, which is 2. 2 to the 0 power, which is 1. We took in the previous video, anything to the power of 0 is 1. And we have 2 to the -1 power, so that's 2 to the -1 power, which is 1 over 2. And then I have 1 over 4, and I have 1 over 8. Now, if I plot these points, we will see some interesting stuff. So let's see here. 3 8s. If I look at the point 3 8, so that's 1, 2, 3, 4, 5, 6, 7, 8. And then I have 2 4, so that's 2, 1, 2, 3, 4. And then I have 1, 2, 0, 1. And then I have -1, 1/2 right there, and -2, 1/4 on there. And what you'll notice is I'm getting values close enough to 0 that it actually becomes really hard. -3, 1/8, it becomes really hard to draw that in there actually. But what I have is I have this graph that is coming down here, has a y-intercept at 1, and then starts flattening out, and it gets flat. And this is really interesting on a couple levels. One, all of my values are positive. I have +1/8, +1/4, +1/2. So even with negative x values, my outputs are still positive. And what you'll notice is I have 1/2, 1/4, 1/8. The further I go along to the left, these negative x values, the smaller my y values are getting, my outputs are getting. And they become really, really small to the extent that it's kind of hard to draw with just a stylus or a pencil and paper. It's hard to draw because it's so close to 0, I can't draw thin enough. But what you'll notice is after my x value of 0, as I move into the positive values, my outputs, my y values start getting really, really large. They get really big. And this is the basic shape of all exponential functions. Now, if I were to change this to be 3 to the power of x, all these values would change, but they would actually behave really similar. 3 to the power of 0 would still be 1, but 3 to the power of 1 would be 3, and then it would be 9, and then be 27. And then it would just be 1 over 3, 1 over 9, 1 over 27. And what you'll notice is when I change that base to 3, my outputs are still all positive. They still get super small the more to the left I go on the x-axis, and they get really large similarly as I go to the right on the x-axis. So any exponential function is going to have this same basic shape. Now, the exact curvature will vary, but they're all the same basic shape. And so we talk about domain and range, and let's talk about domain. I can get really big x values, I can get really small x values, and I'm always going to have an output. Nothing is going to cause this to be undefined. And so the domain is everything from infinitely negative to infinitely positive. I can plug in anything. And range range is interesting because what you'll notice is over here on the left-hand side of this, the negative x values, I get infinitely close to 0. But it's important to note that it never actually touches 0. It's always 1 over something. So it's always a fractional value. And it gets smaller and smaller and smaller, but it never actually touches 0. So we have to use parentheses 0. And how high does it go? Well, it goes really high, really fast. So it's going to go to infinity. This domain and range is consistent for all exponential functions that have an a greater than 1. It's true for all of them. And so we have our basic shape. Now, please note that you can do transformation of graphs, and you'll have questions on this. So go back and look at videos on transformations, a ton of stuff on YouTube. I've posted some videos, but there's a lot of stuff on transformations, but you can do a lot of different things. You can reflect it over the x-axis, the y-axis. You can shift it horizontally, vertically. You can stretch and compress horizontally and vertically. All those things you can do to your parent exponential function. So whether it's 2 to the x or 3 to the x or even interesting stuff like 1.5x, whatever it is, you can still do all those transformations to them. So just be aware of those, that we can do all those different things to the parent function of an exponential. Now, I said it initially in this video, there were 2 categories. One was when a is greater than 1, and the second category is when a is between 0 and 1. Sorry, it shouldn't be equal to. It should just be a is between 0 and 1. So these are fractional values. So fractional values. So we have f of x equals a to the power of x for fractional values, as in like 1/2, 1/3, 1/4. And so there's a couple of things I want to point out. So I have 1/4 to the power of x. 1/4 to the power of x. Now, here's the interesting thing. When we look at a function as f of x equals 1/4 to the power of x, we got to think about our exponent rules. So 1/4 could be written as 4 to the negative 1 power. So if you had something like this, if you had f of x equals 1/4 to the power of x, you could actually write that as 4 to the negative 1 power to the power of x. Now, our exponent laws say when you have powers on top of powers, you can multiply them. So that is 4 to the negative x power. So 1/4 to the power of x is equivalent to 4 to the negative x. Now, if we look at this, the negative x right there, that actually means that 1/4 to the power of x is equivalent to 4 to the negative x, but 4 to the negative x is the reflection. It is the reflection over the y-axis. It is a reflection over the y-axis. 4 to the power of negative x is simply a reflection of 4 to the power of x, which means 1/4 to the power of x is a reflection over the x-axis of 4 to the power of x. And that tells us what shape it's going to take. If you can imagine this, 4 to the power of x would at least be similar to this one. And think about what a reflection over the y-axis would be. It would look something like this. And that is very precisely what this is going to look like. 1/4 to the power of x is going to take the general shape of that right there. So if we make a table, so I have x, and then I have 1/4 to the power of x. And we're going to look at those same values, -3, -2, -1, 0, 1, 2, 3. Well, let's start real easy. To the power of 0 just means 1. Okay, I got that. 1/4 to the power of 1 is 1/4. 1/4 squared is 1/16. 1/4 to the third power would be 1 over 64. And so if I go to plot these values, the easy ones, I got 0, 1 right there. And then I got 1/4, 1/16, 1/64. We are already super, super tiny values. And so that's coming, and it's going to hug, has that horizontal asymptote at 0, getting infinitely close but never touching. But where it gets interesting is the negative side. So 1/4 to the -1 power. Well, remember that -1 power just means the inverse, the multiplicative inverse. It means flip it. So 1/4 becomes 4/1. -2 power means flip it and square it. So that's simply going to be, the reciprocal is 4, and 4 squared is 16. Now hopefully you see symmetry here. So it makes sense then that this one up here is going to be 64. But you have these values, and they very quickly take off. And take off so much, in fact, that I'm off the graph before I even get to x equals -2. It's already way up there. But that is a mirror image over the y-axis of the exponential function we looked at above. And yeah, so we have a very straightforward table. All of your exponential functions that have an a value, a base value between 0 and 1, so fractional values, will take the same basic shape, which is basically a reflection of the y-axis of the multiplicative inverse, as we saw up above. So once again, you can still take transformations of this, and you need to brush up on your transformations to get a good view of this. So domain and range, I can plug in any positive or negative value. There's nothing that's going to blow this up. So my domain is, once again, all real numbers. And my range, although it's facing the opposite direction, it's flipped around, it still gets infinitely close to 0 without ever touching, and it still goes all the way up to infinity. So it is the same domain and range regardless of whether it is greater than 1 or between 0 and 1.